So the basic idea therefore is to, you have the input here, right, and you are trying to divide this continuous time input into many bins, right. You want to classify the input as being in, so when we looked at the quantizer, the range of the quantizer was from minus Vref to plus Vref, and if there are n bits, what we are doing is we are trying to figure out, we are dividing this range into how many bins? If you have an n bit converter and the input range is defined to be minus Vref to Vref, what are we trying to do? What we are doing is dividing this range into many equal bins, where the number of bins is equal to, for an n bit converter, there are 2 to the n bits, correct? And the size of each bin is 2 Vref by 2 to the n, correct? And then we are trying to figure out in which of these bins if the input is, say, so the input is here, right, then we say that the input is in this particular bin. And now since there are a finite number of bins, what we are doing is assigning to each bin a digital word, correct? So if there are infinite number of bins, obviously it's not possible to represent with finite number of bits. So that's why we need to have a finite number of bins, so that for every bin you can assign a digital code. The number of codes required will be 2 to the n, which means that you can represent 2 to the n bit digital code. That's the basic idea in the whole process, right? And as Nagendra pointed out, this process involves some error, right? Okay? And so, in other words, the error is happening because for every analog input in this range, the output is the same output, right? So the output of the A to D converter is basically, it's going to say the input was in the 17th bin, no matter what exactly the input was in this range, right? So clearly, this is quantization and this is an error prone process, and we have gone and calculated, how much error there is and all this wonderful stuff. So, in other words, the basic idea, therefore, is to classify the input into various bins, and a straightforward way of doing this seems to be, this is something which would come to our mind right away, which is, this is the input. I will compare this input Alright. So one straightforward way of doing this, to figure out which bin the input lies in, is to compare the input simultaneously with all these thresholds, right? We want to figure out, so if you divide the input into range into many bins, each one of these, for example, can be V3 and so on. So if the input belongs to a certain bin, correct? What do you think this suggests? If the input lies in a particular bin like this, we know that the input lies between V2 and V3. What do we expect for the output? If the input lies between V2 and V3, then if you compare the input with V2, you should get let's say you have a building block which we call the comparator, whose job is the following. So V in, Vx, V out, right? So if V in is greater than Vx, V out is a logic 1. And if V in is less than Vx, V out is logic 0. So let's assume that we have a building block like this. Okay, so this is what is called a comparator, and the name is pretty obvious because it compares two inputs and just makes a decision whether the input is either smaller than Vx or larger than Vx. We'll see how we can build circuits to do this, make this happen going forward. But let's assume that we have a block like this. You understand? So this is like going to an interview. You either cleared it or not, right? What happens inside the committee room, nobody knows. Okay? So as far as the input and output is concerned, if you're less than a certain threshold, it is a logic 0. If you're greater than a certain threshold, it is logic 1. Okay. Now, given that we have these things, how would we use these elements to do an A to D conversion? So clearly, in other words, what we want to do is we want to figure out if the input lies in a certain bin. Correct? In other words, we want to find out if Vn lies in a bin bounded by V1 and V2, okay? This is the question we are trying to answer. So, given that you have elements called comparators which behave as shown in the top, what do you think we can do? Yes? Yes. So how will you do this? You have two comparators, right? Correct? So so let me call this, this is V1, and this is V2, and let me just assume that V2 is greater than V1. So X and Y are two logical outputs. If Vn lies between V2 and V1, right, what can you expect? How can you know for sure that Vn lies between V1 and V2? Pardon? This, you can be absolutely sure that Vn lies between V1 and V2 only if, come on people, if X is 0 and Y is 1. Only under this condition will the input lie between V1 and V2. Correct? If both of them show 1, what does it mean? The input is much higher than both V2 and V1. Clearly V2 is greater than V1, so the input is much higher than V2. If both of them show 0, then you know that it is less than V1. And if V2 is greater than V1, in principle you will never get, please note, you will never get, if there are 2 bits, they can in principle take 4 values, 0, 0, 0, 1, 1, 0 and 1, 1. So, if both show 1, 1, we know clearly that the input is much larger than V2. If both of them show 0, 0, both are less than V1. Okay. If X shows 0 and Y shows 1, it is within this bin, which is between V1 and V2. What if X shows 1 and Y shows 0? So please note that is not possible, because if we know that V2 is greater than V1, right? That possibility should never occur, right? Okay. So X, Y, so 0, 0 means input is less than V1. 0, 1 is not possible. Right? 1, 0, 0, 1 is possible, right? And this means that Vin is less than V2 and greater than V1. 1, 0 is not possible. And 1, 1 means input is greater than, right? So to figure out if the input lies within a certain bin, you need 2 comparators. Okay? Does it make sense? Okay. Now we are just not interested, we are interested in making an AD converter or a quantizer. We are not interested in just figuring out if the input lies within one bin. We want to figure out if the input lies, we want to figure out which bin the input lies in. So what do you think? How can we extend this idea? So in other words, looking at the logical outputs of X and Y, right? We should be able to figure out if the input lies in this particular bin. Now if you copy and paste this for all particular bins, for all bins, right? You'll be able to figure out in which bin the input lies. Does that make sense? Correct? In other words, if I took, so this is the basic unit which answers the question, does the input lie between V1 and V2? Right? And how will I figure this out? If I want a 1-bit answer, right? Does the input lie between V1 and V2? What should I do? This is X and this is Y. What should I do? No. The only way, the only answer possible which will indicate that the input lies between V1 and V2 is when X is 0 and Y is 1. So if I want a logical output, what will I do? I want to compute. No, is this going too fast or too slow, or is it? Yes. X bar Y. Right? Okay. So if I now put this in a black box, right? The output of this box is going to tell you whether the input lies within V1 and V2. Correct? Now, obviously the input, at any time can only lie in one of the 2 to the n bins. It can't lie in more than one bin at the same time. Correct? So what should I do? If I want to figure out in which of the bin the input lies in, what should I do? So this logical output will go to 1 only when the input lies in the first bin. Correct? If I want to now figure out if the input lies in the second bin, what should I do? What are the thresholds of the second bin? V2 and V3. So I have to compare with V2, compare with V3. Do I need 2 more comparators or can I reuse some of the hardware? Yes. We only need 1 extra comparator because we've already compared with V2. Is that clear? Okay. So in other words, V3, alright. So this we now need to compare these two, right? What will you do? Again Z bar X, and this will give you a logical 1 if the input lies between V2 and V3, and we can go on like this. Okay? So in other words, once you're basically done, what you will therefore end up having is the following, which is this is V in, and then you have V1, V2, V3, blah blah blah. Correct? And at every point, what are you supposed to do? You're supposed to do the knot of the comparator on top ANDed with the decision of the comparator below, and so on. So if you want to divide the input into 2 to the n bins, how many comparators will you need? Yeah, number of bins is 2 to the n, correct? So how many bins will you need? And how many comparators will you need? 2 to the power n minus 1. Correct? So to divide the range into 2 bins, you need only 1 comparator. Correct? If you want to divide some range into 3 bins, into 4 bins, for example, right? So this is 1 bin, 2, 3, and 4. How many comparators do we need? 1, 2, and correct? So you need. So there will be 2 to the n minus 1 of these comparators. Does make sense? Okay. And not only that, and you're comparing the so now at the output of each of these comparators, you're using this logic by looking at the decisions of 2 adjacent comparators and making a logical output. Correct? So there will be, for example, in this case, there will be how many bits at the output? There is a one wire here, right? And there's another wire here, correct? Okay. In general, if there are 2 to the n minus 1 comparators, they are going to be 2 to the n minus 2 of these lines coming out, right? Where each of these lines is telling you some story. Does it make sense? Okay. Now what, can you make any comment on these, on the logical values of these lines coming out? As we said, what does this mean? That logical value at the output of this gate, okay? What does it mean? That will be 1 only if the signal is lying between, for example, this chap will be 1 only if Vin is lying between, no, look carefully, V2 and V, correct? Alright. So, clearly the input cannot lie in, one single input can lie in only one bin, right, at a time, correct? So, clearly it means that the output, if you have, if you have many wires here, as we do, what can we say about the, at a time, even though you have many wires, only one of them will be high, all the others will be low. That makes sense because the input is only lying in one bin at a time. It can't keep lying simultaneously in 4 bins. You understand? So, on the other hand, what about the logical values here? Let's say the input was let me just now simplify matters and okay. So V1, V2, V3, V4, V5, V6, V7 and Vin goes everywhere. Okay. So, let's say the input is lying between V4 and V5. So, in other words, the input lies somewhere here. So, can you comment on the outputs of the comparators? Pardon? Yeah, that you can do very easily, right? Because you know that if you restrict the input to lying between 0 and Vref, right? Then you know that if it is greater than V7, we know automatically it has to lie in the last bin. Similarly, if it is less than V1, you know that it has to lie between 0 and V1. So, what he is asking was, don't you need another extra comparator which will compare Vin with Vref, right? Okay? That, clearly that's not necessary because we can reuse the output of the topmost comparator. Okay. So, if the input lies between V4 and V5, can you comment on the outputs of the comparators, the logical outputs? It will be, this will be What will this be? 1. Input is greater than the reference. V1 is smallest, V7 is the largest. So what will it be? 1, 1, 1, 1, 0, 0, 0. Okay? So what do you think is so special about this? Is there something you can see there? For any arbitrary input, can you make a comment on the outputs of the comparators? Can it be any random digital word, or is it like, is there some
consecutive words and then impedance 0. And transition is what we do.
Yes. Right? So one thing as we all observe is that the output of the comparators will be a string of ones followed by a string of zeros, and where this transition occurs from all ones to all zeros is where the input lies. Does that make sense? Okay. In other words, if the input is low, the height of the ones column is small, zeros become large. If the input is large, the height of the ones becomes high, and then, okay. So this is very similar to how one, if you take a thermometer and stick it in your mouth, right? The height of the mercury column depends on the temperature, right? So if you have a good thermometer, the mercury column will be continuous and it will keep rising depending on the temperature, right? So inspired by that, this is often called, such a code which is all ones followed by all zeros, is called a thermometer. Okay? Alright? And as he pointed out, one can use, the outputs of each of these AND gates, only, what will be the output of the lowest AND gate there? For this particular input, 0, 0, 0, 1, 0. Okay? And the logical outputs of these AND gates indicates, from that you can go and trace back which bin the input was it. The key point as far as this digital word is concerned, right, is that what is so special about this fellow on the right? Only one of the 2 to the n minus 2 lines is 1. Correct? So, and we know that each one of these lines indicates which bin the maps to a particular input bin. Does that make sense? Correct? But one thing we have forgotten is to figure out if the input lies in the lowest bin or the highest bin, right? So that is very easy to figure out. How do you know if the input lies between 0 and V1? If the first comparator is 0, correct, then what happens? Right? If the first comparator is 0, then you can use that information to infer that the input lies between 0 and V1. Okay? And you could just simply invert the output of the first comparator, and that will give you the stuff for the indication that the input lies between 0 and V1. Similarly, what do you think I can do to figure out if the input lies above V7? Yes? You just take E7, right? So the first and the last codes are, you can this is a logical one, right? And this becomes So clearly you see that we have 7 comparators which divide the input into how many bins? If you have 7 comparators, how many bins are there in the, how many? If you want to classify it into n bins, I mean whatever, 2 to the n bins, you need 2 to the n minus 1 comparators. So in other words, if you have 2 to the n minus 1 comparators, then you will get 2 to the n bins. So you have 7 comparators here. So how many bins do you have? You have 8 bins. So this corresponds to a how many bit converter? It's a 3-bit converter. Okay? So, and so if you want to classify the input as into 8 bins, so how many lines must come out here? There are 8 bins, right? And you have 8 wires coming out. At any point in time, only one of these 2 to the n wires is high, so, right? So this code has also got a special name. Of course, nothing great about it, but this is called a 1 of 2 to the n code, right? So even though there are 2 to the power n wires, right, only one of them is high at any one time. So you can't arbitrarily have different logical values for each wire. Okay. So this code is called 1 of 2 to the n code, just like how the code at the output of the comparators is called a thermometer code. But okay, so but finally what is the resolution of the word that we need coming out of the whole converter? I mean, how many, if you're classifying the input into 8 bins, what is the minimum width of the digital word that you need to represent 8 bins? You need 3 bits, correct? So one you assign for every bin, you assign a code word. There are 8 bins, you assign 8 code words, which means that you can do with just 3 bits, right? So all that you need to do therefore is to have some logic here, right, which takes this 1 of 2 to the power n code and generates from this a 3-bit word. Okay? So what is, what do you think this is called? The encoder, right? Correct? This is straightforward to do. I mean, all of you know, most likely know how to do this. This is just combinational logic, that's all, right? If this particular wire is high, you put out, in what bin does it lie? 0, 1, 2, 3, 4, right? So you put out a code 100. That's all that you need, correct? So the flash A to D conversion process, therefore, right, is basically, if you have n bits, this is what you do, right? For a 3-bit example, I can draw it on the board. There are 7 comparators. If you have a 6-bit A to D converter, how many will be there? 2 to the power 6 minus 1, which is how much? 63 comparators, right? If you want to build a 10-bit flash converter, how many will be there? 1023, right? So if you want to build a 16-bit comparator, how many will be there? Some long, very big number, right? You understand? So what do you see? The complexity is exponentially related to the number of bits. Correct? That's one thing that has come out immediately, right? Okay? So hardware complexity is related to 2 to the n. Strictly it is 2 to the n minus 1. But if n is large, whether you have 65536 or 65535, hardly makes a difference, right? So that is the first thing that comes out. So if you want to increase the resolution, right? If you want, for example, to reduce the step size by a factor of 2, how many extra comparators would you need? Reducing the step size by a factor of 2 means that I have twice the number of steps, which means that I need twice the amount of hardware, right? And twice the number of steps is equivalent to resolution wise how much?
1 bit at a time.
Yeah. Yes. Do others see this? If I increase the number of, have the same range, if I reduce the step size by a factor of 2, right, then I will have twice the number of levels, correct? To have twice the number of levels, I need 1 bit extra to represent twice the number of levels. So it translates to an increase of resolution by only 1 bit. So 1 bit increase in resolution requires 2x the hardware complexity. Do you understand? Okay? This is what it means. So, what do you think? So if this is the situation, can you comment on the practicality of doing things using a flash converter for high resolutions? I mean, in other words, if I wanted to design a 16-bit converter, do you think I would try and use a flash? Pardon?
If possible, do other way.
I mean, it seems like, if you get just one more bit, if I have to, double everything, okay? It seems like a very expensive thing to do, okay? Which is why people, generally it makes sense that you do not use flash if the resolution required becomes higher and higher, okay? So, usually people stop when this 2 to the n starts becoming a painful number, right? And so if you want to do up to 6 bits, this is a reasonable thing to. Okay, we'll figure out why this is a inefficient way of doing it as we go along. You understand? So, one question that one might ask is that, okay, fine, there's all this hardware. Am I gaining something, right? Is there usually most things in life have both pluses and minuses, isn't it? It's only very rarely that you come across something where there are only positives or there are only negatives, okay? So, hopefully, this is the negative is that the hardware complexity increases exponentially. Is there something is there some good thing you can say about the flash? Yes? Why? Okay. So, speed is good or bad? Good. Why? Why is it very fast? Pardon? Right. So, as you all said correctly, the good thing is the speed of conversion, right? So, what is the total delay of the flash? How long do you think it will take for you to get the code word out? How long does it take for you to figure out the answer? Pardon? It is the delay of, total delay is simply T comparator, correct? This T comparator is what? The time taken for the comparator to tell you whether the input is less than something or greater than something, plus 2 levels of 2 gate delays, right? This is a rough estimation of how long it takes for one conversion to occur. So if it takes so long for one conversion to occur, what does it mean? How fast can the converter run? If it takes 1 nanosecond for all this to happen, then it follows that after 1 nanosecond, this follows all this hardware sitting idle. So you put the next input, right? So the maximum speed is basically 1 over T comparison plus 2 gate delays. Okay, in principle. And what is T comparison? Can you estimate T comparison? Will it be 1000 gate delays or will it be roughly of the order of a few gate delays? Well, finally, what is the logic gate doing? If you have CMOS inverter, what is it doing? It is comparing the input to some threshold and then putting out a logical 1 or a logical 0. So it follows that if an inverter can do it in a gate delay, right, then it follows that this comparator, which is comparing, 2 inputs, Vin and Vref, whatever, Vin and V1, Vin and V2 or so on. Okay, maybe it takes a little more time, but it cannot take too much more time than an inverter, right? So in other words, all that I am trying to argue is that this time taken for comparison should be of the order of a few gate delays. It cannot be very, very long. It can't take very much longer than an inverter delay. That's what I am saying, right? Maybe 2, 3, 5, all these are roughly of the same order of magnitude, right? So as you can see, the speed that's possible is actually very, very high. Does it make sense? Okay. Now, can you intuitively tell me how we are getting this, why we are getting this such a high speed? So you can see that there is a lot of parallelism in the flash, because simultaneously you have in a 6-bit flash converter, for example, or in this 3-bit example, you have 7 people who are simultaneously looking at the input and telling you whether the input lies in this bin or that bin, or another way of doing it would be to do it serially, right? So you have only one comparator, right? So you say, hey, does the input lie between V1 and V2? If it does, then I'm done, right? But and then I will say, if the input doesn't lie between V1 and V2, what should I do? It's not there between V1 and V2. What can I do next? I'll check between V2 and V3. Check between V3 and V4. That is, that is basically dumb search. Correct? Okay. So finally, A to D conversion is equivalent to searching, right? In which of these 2 to the n bins the input lies. Okay. And this is an example of a parallel search where you have 7 fellows simultaneously looking and telling you if the input is here, the input is there, the input is there. You understand? Okay. And then you look at the outputs of each of these 7 guys and then figure out if, from that you can figure out in which bin the answer lies. Correct? Because only one of those fellows will finally, looking at their answers, you will be able to figure out where this transition from all the ones to all zeros is occurring. Right? So this massive parallelism is what is responsible for the high speed. Right? It is also responsible for hardware complexity, because you are replicating this stuff many times. Does this make sense? Okay. Seems like a reasonable trade-off. Correct? Okay. Alright. So that unfortunately restricts the flash to applications where the resolutions are modest, right? So 6-bit precision is not, if you think about it, it is about 1 in 64, which is about 1.5%, right? Okay. So in applications which require low to medium resolution, a flash is used if you need very high speed, right? In other words, you can't say, you give me the input, I'll tell you the code tomorrow, right? Okay. And presumably, if you can take a lot of time over something, you can do it efficiently. Okay. But if you want the answer now, it follows that, you can't, you have to pay a price in terms of complexity and power. Basically, more parallel blocks means more area and more power, because you have to pay all their salaries, right? So, they simply can't be, they're all there, right? And you're paying bias current every time you run a block. So, this is only used in applications where, speed is absolutely critical. And when do you think speed is, in what applications do you think speed might be a critical issue? Pardon? Real time, especially when things are in a part of a feedback loop. Correct? For example, many applications are where this converter is put. The A to D converter is a part of a feedback loop. So you're measuring something and then you're doing some DSP and then figuring out if what you're measuring is correct or not and going in and changing something. Correct? So whenever you have a feedback loop, then what happens? If there's too much delay in a feedback loop, what happens? If you have too much delay in a feedback loop, what happens? Pardon? Yeah. So finally, if there's too much delay in a feedback loop, what happens? The system becomes unstable. That is a serious problem, right? The system is working but not efficiently, you might be able to accept. But if you put, this is feedback with too much delay. You understand, right? So, whenever you have a feedback loop and there's a lot of delay in the loop, then the loop will become unstable. Delay and phase are pretty much related, correct? So, if there's a lot of phase in the loop, then the phase margin in the loop goes down, and if the phase margin becomes too small, you have instability. So, in applications where the A to D converter is embedded as a part of a feedback loop, right, you cannot take too long to decide what the input is. So, a flash converter is often used even though it is inefficient, because you want the output now. You understand? Okay? Right? Okay. So, a classic example of an application of a flash converter is basically in hard disk drives. So what happens is that the signal that you get from the read head is some very small signal. Right? So there's a magnet. Yes, sir. Yeah. Go ahead. Let me just. A classic example of the use of a flash converter is in all our hard disk drives which are there on a computer, right? So hard disk drive is basically a platter of magnetic material. Stuff is coated on it, and then you want to basically, store obviously as much information as possible on the drive, correct? So what they do is the drive is made up of magnetic material. If you want the magnet, this tiny magnet on the drive is oriented in one way. If you want a 0, it is oriented in the other way. So as you keep reading the drive, what you're basically doing is measuring the voltage induced by this magnet okay, in a coil, roughly that's what it is, right? So if the magnetic domains, so the voltage will be a very small value, something like this, and from this value you had actually figure out whether what was written was a 1 or a 0, okay. So it turns out that clearly if you, one way of doing it is to basically write these things so far away, right, that, it's very clear if the magnetic domain is oriented in this direction or in the opposite direction. But unfortunately that means that the density with which you can pack information becomes very poor, okay. So what people do is you try to pack as much information as possible. In other words, the separation between the directions of the domains is actually very, very small, okay, and this way you can pack a lot of information, right, and you use electronics and DSP to be able to look at these small differences and then still be able to figure out what data was written, right. So clearly if the data, if some read waveform is looking like this, then you know that if I can look at something with my naked eye and tell you it is 1 0 1 0, then clearly there must be a more efficient way of storing information, correct? So what you can do is basically, let's say I squish the distance, then what happens is it will barely go to 1 and then come back to 0 and then, something like this, right? So in this amount of distance I have actually stored more information, right? Now, obviously it's less obvious to the naked eye what it is, but you can, use complex signal processing algorithms to figure out. So what happens in a display platter, therefore, is that there is this analog signal coming from the read head. This is very small, so this is amplified, right? And then from this you have to digitize it, okay? Alright, which means sampling and quantization, right? So I'm going to explicitly put the sampler and this is the quantizer. This goes into DSP where they look at these samples and then try to unravel what bit sequence was written onto the drive. Unfortunately, you can see that this is an analog signal, so the signal is probably like this, okay, and this sampling is happening here. It is very likely that, for example, you're sampling at the wrong instant. So let's say this is a 1 0 1 0 stream, right? Ideally, where do you think we should sample? You should sample at the center of the bit, correct? But in the beginning you will not know where to sample, so you just keep sampling, and let's say you landed up with sampling here, okay. If you just look at those samples, you will think that the data written is all zeros, right? Or you can't make any sense of the input at all because it always seems to be 0. You understand? So in other words, by looking at the samples, you also not only need to figure out what data was written, you also need to know where to sample, correct? So based on this, what happens is that the sampling instant, if you don't understand it in great detail, don't worry about it. What I'm trying to say is that the sampling instant of the A to D, the sampling frequency is known, but the exact sampling instant also needs to be known. The phase of the sampling needs to be known, correct? And that has to be figured out only from the samples at the output of the DSP. For example, if you know that you're getting all zeros at the output of the data converter, you know clearly that you're sampling in the wrong phase. So you're going to adjust the phase, okay, to get back to the center of the bit. Okay. So clearly you can see that this is a feedback system. And not only that, you also need to adjust the gain, because depending on where you are in the platter, the gain of the head and all that will change. So you can see that all these things, there is a massive feedback loop through the A to D converter, through the DSP and back. Okay. And if you have too much delay in the A to D converter, you will have the loops will become unstable. These are all feedback loops which will simply become unstable. And today, can somebody guess what the rate at which you read data from a hard drive is? Pardon? No? I mean, if it is 10 megahertz, then, by the time you read, you load a file, it will take forever. So, laptops will typically have 700 to 800 megabits per second drives. High-end desktops will probably have something like 2 gigabits per second, right? So, you're able to read data from the drive onto your, PC, onto the board at rates which are exceeding a few gigabits per second, right? So, 1, 1.5, 2, and this number goes on increasing, okay? So, in other words, this A to D converter is to sample at those speeds, right, which is like say, today it's now common to see, 1.5 gigabits per second A to D converters, okay, and which means that the amount of time that you have to convert is 1.5 gigabits per second means that you have 600 picoseconds to sample, figure out, which of these bins the input lies in and put out a digital word, and then 600 picoseconds later you have to be ready for the next input. Okay. So, an extra clock cycle of delay in the A to D converter can make the whole system not work at all because of the delay introduced by the data converter. Alright. So, typically in disk drive systems you have 6-bit converters at several gigabits per second. Okay. So,
is the sampling rate then only to optimize the VLSI?
Oh yeah, of course. I mean, so the challenge so from an architectural level, a flash converter is a very simple thing. It can't get any simpler than, right? So if you look at it, the only thing that we need to do, we have in fact figured out everything else except what? The encoder is combinational logic. It's straightforward. Right? You have gates. The only thing we need to figure out are how to do a comparator, right? Or how to build a block which will compare two inputs, and obviously there must be some trade-offs involved, right? Obviously, whatever you try to do, you always find that you can't do as good a job as you want. So there must be an understanding of what non-idealities there are in the comparator, how they affect the performance of the converter. Okay. So, what are we? Is time for lunch or what? Okay. All right. So let me just quickly summarize in a couple of minutes. Basically, what we have is you need an array of comparators, right? And this will put out what kind of code will the array of comparators put out? It will put out a thermometer code. Then you need some logic to put, and this puts out a 1 of 2 to the n code. And then you have a encoder which puts out the n-bit word. So this is the block diagram of a flash ADC, right? That we have discussed so far. So I'm not going to discuss this or this. So we need to go and look at the array of comparators, which basically means that we have to figure out how to design a single comparator. Once you have designed one, you copy and paste so many times and then you have the entire thing. So one more thing that I'd like to point out is that the regularity of the structure, right? So this logic is basically simply nothing but for each slice of the comparator, it is basically you have of the flash ADC, you basically have one comparator, some logic gate, and it goes to the encoder. So the design usually proceeds as follows. So you just design this part and then copy and paste so many times, and then you look at these this 102 to the n code, push that into an encoder, and out comes the bit. Okay. So the crucial thing is therefore to look at the comparator and see what we can do to how do we realize this using transistors. Okay. So we'll see that in the